Greetings everyone, and thank you all for joining us for today's AMA on the AMD Ryzen 5000 series of processors. I'm Mithun from Digit and I'll be your host today. This session is sponsored by AMD and the materials being presented today have been provided to us by AMD. We'll be delving into the details of the microarchitecture, looking at performance in gaming, content creation, and other important areas. And we'll be looking at some of the important features that the AMD ecosystem has thanks to the introduction of Zen 3. The content will be centered around performance improvement attained by Zen 3 over Zen 2. And if you wish to get more information regarding Zen 3 processors, then we've also reviewed two of the Ryzen processors, and the review is live on our website. So you can always head over there and get more information. We'll switch over to the slides and move on. So we're starting off by looking at the journey of AMD's Zen microarchitecture. It started off back in 2017 with the first Ryzen 1000 series of processors, which were all on the 14 nanometer process by FinFET, TSMC. This was followed by Zen Plus, which moved to the 12 nanometer process, which was a bit more power efficient. And the introduction of the Ryzen 1000 series, that is the first Zen microarchitecture, brought with it a 52% IPC uplift compared to the previous generation. And the previous generation was Bulldozer and Excavator. Now 52% is a massive increment in the domain of processors for IPC. And in case you're wondering what IPC is, it stands for instructions per cycle or instructions per clock. Then came Zen 2, where we saw another 15% IPC uplift and the move to a more efficient 7 nanometer process node. And in November this year, we saw the introduction of Zen 3, that is AMD's latest microarchitecture, which is a ground up redesign that has resulted in significant performance gains and also happens to be the topic of today's AMA. So at the onset, AMD had three design goals for Zen 3. These were to increase the performance by focusing on IPC, and closely tied to that was the objective to reduce latency between the cores. And the third, we have efficiency, which is considered in terms of performance per watt. It is one of the ways of looking at efficiency, and that's always paramount when you're looking at processors. Now, once we have these design goals out of the way, let's take a look at the major changes that were incorporated in Zen 3 versus Zen 2. Now, this was a ground-up redesign, so there were a lot of different changes. All of the elements that you see in front of you have to be balanced. So an improvement in one aspect is closely tied to another element of the microarchitecture, and the two need to be tweaked in order to get a good performance gain overall. Most of the improvements that we see here are concentrated in the front end, followed by the execution elements, and then in the load store aspects of the processor core. The front end deals with the branch predictor logic, how the instructions are fetched and then broken down into macro ops before being sequenced within the integer as well as the floating point pipelines. We see that AMD has improved bandwidth, and it also has tweaked with the sequencing of instructions, which is now done in a much faster fashion and with finer grained switching. Then we have the execution part, which deals with the actual operation being performed on the operands, that is where all the instructions are run. We see improvements with both the integer as well as the floating point pipelines. Latency has also been reduced for certain integer and floating point operations, and the dispatch, which is the bit over here, is wider, and FMAC, which is an instruction, has been sped up by reducing by one cycle. Then we get into the load store elements, that is towards the end, which also show bandwidth improvements along with more flexibility in dealing with varying operations. More resources have also been added for the TLB, that is the translation local site buffer. And overall, this is a brief overview of the major changes between Zen 3 and Zen 2. If you have any questions, please let us know in the chat and we'll come back to the slide later on. Now, how massive an improvement was attained is the major topic of discussion. AMD has stated they've managed to get 19% IPC uplift. Now, what this means is that compared to Zen 2 processors, Zen 3 processors can execute 19% more instructions per cycle. This simply means that you'll get more performance within the same amount of time. IPC, along with frequency, is what determines the performance of your processor. So when you combine high IPC along with high frequency, you get much higher performance gains, and you'll see those in the slides to come. Before we do that, let's see how all of these changes that are listed over here have contributed to the overall performance gain. The 19% figure is achieved by taking a Zen 2 processor and a Zen 3 processor, running them at the same fixed frequency of 4 GHz, using the exact same setup, and then running multiple workloads to see how much performance gain is observed in each workload. So in effect, this 19% figure is a geometric mean of the results obtained from 25 different workloads. In this graph, we can see the front end, load store, and the execution engine have contributed the most to the performance gains. This is followed by the cache prefetching, micro-op cache, and the branch predictor. Now that we've seen the breakup of the 19% uplift, let's take a look at all the different workloads that were tested in order to get to this magic figure. Now, I'd like to state again that these numbers were obtained by comparing a Zen 2 processor with a Zen 3 processor in the same system, with both processors clocked at 4 GHz. Here we have a mix of different CPU intensive workloads comprising of gaming, content creation, virtual reality, and 3D modeling. This is coupled with a lot of popular industry benchmarks, which we are all familiar with. If you've observed the different workloads, then you'll see that 14 of these graphs are for video games, and that tells you where the Ryzen 5000 series of processors really excel. Most video games tend to use about 4 to 6 CPU cores, and having performant, low latency cores works out in favor of most AAA titles in the market. You'll also see that there's a mix of APIs used in each of these games. We see Vulkan, DirectX 9, 11, and 12 represented. Also, a lot of the games shown here use different game engines. So you have high performance gains across different graphics APIs, and they're all running on a variety of game engines. Now, video games in general favor low latency and high performance cores. So let's take a look at another major change made in Zen 3, which helped in this aspect. Now here we see the core complex present within each CCD, that is the core compute die. On the left we have Zen 2, and on the right we have Zen 3, which powers the newly released AMD Ryzen 5000 processors. In Zen 2, each CCD, that's this aspect over here, has 2 CCX. You have one in orange, one in pink. Each CCX in turn has a maximum of 4 cores, and each CCX also has 16 MB of L3 cache, that's level 3 cache. If the cores from this particular CCX need to talk to cores of this CCX, they have to go through an interconnect in the middle. In Zen 3, you have 2 CCXs which have been combined into one, and each CCX has a maximum of 8 cores. And the entire CCX has access to the entire 32 megabytes of L3 cache. So over here, each of these cores could only access 16 megabytes of L3 cache and took a little convoluted path to get here. Whereas in Zen 3, each core has access to the entirety of the 32 megabytes of L3 cache. That reduces latency a lot, and there is no need for any of the cores to use the interconnect to talk to the other core. And we'll see how this happens in the next slide. Over here we have the Zen 3 cache hierarchy. Each core has a 32-byte instruction as well as a 32-byte data cache, followed by 512 kilobytes of L2 cache, and those in turn talk to 32 megabytes of L3 cache, which is also called a victim cache. If any of the core have to talk to each other, let's say core 0 has to talk to core 7, then they can do so quickly since the entirety of the L3 cache is now combined. in the previous cache, in the previous scenario, you had to go through an interconnect to get into the L3 cache of the other CCX and then talk to the other core. Now, this was a close-up of the CCX hierarchy or other topology. And next, we'll be seeing the topology of the entire processes from the CCD and CIOD perspective. So these are the two chiplets along with the IO die. In case you've seen the first slide, let me bring that one up. You can see this is how a Zen 3 processor looks like when you take off the heatsink on the top. So each of these little things are the compute chiplets, and this is the IO die. Coming back, so you can see how the CCDs are interconnected with the CIODs using Infinity Fabric, which is AMD's interconnect technology, which is very fast and tied with DDR4 RAM frequency. And then the CIOD communicates with the RAM. So that's how your entire communication happens within the processor and the memory. Moving on, we can see that Zen 3 has the 19% uplift, which we've gone through multiple times over. This was calculating with two processors set at 4 GHz, that is Zen 2 and Zen 3. And here, in this particular slide, we are doing away with that 4 GHz limit, and we are comparing a Zen 2 processor at its advertised speed with Zen 3 processor at its advertised speed. Now, this is a gaming benchmark chart, and here we see that the Ryzen 9 3900 XT compared with the Ryzen 9 5900X. Both CPUs have 12 cores and 24 threads. The 3900 XT has a boost clock of 4.7 GHz, while the 5900X has a boost clock of 5.8 GHz. We see gains of up to 50% in titles like League of Legends and CSGO, and we also see some modest gains in games like Battlefield 5 and Total War 3 Kingdoms. These two processors were released 4 months apart, so you can see how significant gains are. Moving on, we see the gaming performance gains with the 5900X as well as the 5950X. These are the two top-end SKUs that AMD has this time. We see that most games perform better on the 5900X versus the 5950X. Now, this is because video games in general favor lower latency processors, and the 5900X has fewer cores in it, which is why you have lower latency, because fewer cores take fewer time to talk to each other. Moving on, we'll be looking at the current lineup of the entire Ryzen 5000 series. We have 4 CPU models with us. The Ryzen 5 5600X, that's a mid-range CPU, followed by the Ryzen 7 5800X, which is also a mid-range processor, but towards the higher end of it. Then you have the absolute top-end Ryzen 9 5900X and the 5950X. You will see the processors being compared to their predecessors from the Zen 2 microarchitecture-based Ryzen 3000 processors. Across the board, we see double-digit growth in 3 processors, and what stands out is the 18% improvement between the mid-range 3800X T and the 5800X. Again, these two processors were released 4 months apart. So within 4 months, getting 18% of performance uplift is quite significant. This particular test was Cinebench R20, and this is a multi-threaded performance benchmark. So a lot of reviewers, including us, we use Cinebench R20 to highlight single-threaded as well as multi-threaded performance gains between processor generations. Now, moving on, we have Cinebench again, which is the benchmark that we were talking about. And one aspect that we'd like to point out is up until Zen 3, we never saw CPUs cross 600 points in Cinebench R20 while running under stock conditions, not overclocked. This is the first time that any processor has crossed the 600 point barrier. Ryzen 9 5950X is at the lead with 640 points, followed by 629 points for the 5900X, 617 points for the 5800X, and the 5600X is a few points shy of hitting 600. But majority of the processors that you've seen in the first launch cycle of the 5000 series have broken the 600 point barrier. On the left, we can see the AMD Ryzen 9 3900 XT, which was released 4 months ago, and we can see it scored 456 points. And we also have a competition processor just for reference. Moving on, we're going to look at DaVinci Resolve, which is a popular video editing application that includes tools for color correction and audio and video post-production. It's a holistic suite when you're looking at video content creation. When Zen 2 is compared with Zen 3 in DaVinci Resolve, we see between 8 to 10% of performance gains. So content creators can use this particular information to judge if they'd like to upgrade from Zen 2 to Zen 3. Now, since we are the topic of upgrading, Zen 3 is a drop-in upgrade. What that means is that if you have a compatible Zen 3 motherboard, which is a B550 or an X570 motherboard, then you can simply update the BIOS to a Giza 1.0.8.0 and remove your Zen 2 processor and swap in a Zen 3 processor. That's all you need to upgrade from Zen 2 to Zen 3, a simple BIOS upgrade. The entire platform can remain the same. You don't need to change anything else. Now, we've looked at a lot of performance graphs overall, and most of them were focused on gaming. We looked at one which was around DaVinci Resolve and some industry benchmarks which focused on 3D rendering and movie creation. Now we are going to look at the graphics card along with the AMD processor. This is because AMD also announced the RDNA 2 based Radeon RX 6000 graphics cards on the 18th of November this year. And when you combine a AMD Ryzen Zen 3 processor with a Radeon RX 6000 series graphics card, you can get a little extra performance by switching on something called AMD Smart Access Memory. To do this, you'll need, again, a B550 motherboard or an X570 motherboard, since those are the ones which support Zen 3. Then you need to upgrade the BIOS again to a Giza 1.1.0.0 and switch on two options within the BIOS. One of them is called above 4G decoding, and the other one is called resize bar support. Resize bar support is a feature that's present in the PCIe Gen 4.0 standard, and what that does is basically allows the CPU to access the entirety of the GPU memory. This removes bottleneck and improves performance. Then again, we should also point out that game developers, if they want to make use of AMD Smart Access Memory, they'll have to make changes to their game engines and to their game overall. Over here, we see an average of 6% performance gains when you switch on Smart Access Memory. That is, when you have an AMD RX 6800 XT compared with the 6800 XT without SMA or SAM switched on. And this can vary across every single game. Sometimes you might actually see reductions, but the maximum so far attained has been 11%, and that's in Forza Horizon 4 running at ultra configuration. So it's not even at low configuration. So that's again quite significant. Moving on, we now come to Precision Boost Overdrive 2, which is a new boost technology algorithm that builds upon the benefits of the first iteration of this technology, which was called Precision Boost Overdrive, or PBO. That's what we're going to refer to from the next slide onwards. And it deserves the existing benefits which we've gone to and gives you more performance by introducing something called undervolting in a much simpler manner. So not only enthusiast overclockers, but even the average Joe can sort of experiment with undervolting now. So over here we see that Precision Boost Overdrive is targeted towards practically everyone, but enthusiasts and overclockers who would like to get a little extra performance are going to benefit vastly from it. It introduces a new tool called the Curve Optimization Tool, which tries to opportunistically reduce voltage whenever possible. Now, this could be during low load situations or even during high load situations. The AMD Zen processors have something called a system management unit, within each processor, which constantly monitors a wide set of parameters in order to understand when it can apply these optimizations. Now it looks at voltage, temperature, and frequency among other parameters, and whenever it can, it will try to reduce or optimize the voltage frequency curve. The SMU, which is a system management unit, is capable of performing this operation every millisecond. So that's 1000 optimizations being done every single second. And that can have tremendous gains in certain applications, not so much in something else. It really depends on the kind of headroom that you have, which again varies when you have high load versus low load. Also, it varies from processor to processor, as you'll see in the next slide. Now here we see three graphs, okay, and three graphs per processor. Very first one, which is the gray colored one, is the stock one, which is with no bias settings touched whatsoever. We're running the 5800X as well as the 5900X at their stock frequencies. And then you have the middle graph, which is precision boost overdrive, which was the previous iteration of PBO2, along with a 200 megahertz boost override. So whatever boost that the processor is advertised for, you're adding 200 megahertz on top of that. So with that, you can see there is no gains between the 5800X running on PBO with the 200 megahertz boost override versus the stock. And in the case of the 5900X, which has a lot more cores, you see that the precision boost overdrive along with 200 megahertz boost override has around 540 point increase. So that's quite significant right there. And then we have the third graph in both processors, which is with PPO2 activated. And we now see gains in both processors. In 5800X, the score goes up to 6095. This is Cinebench R20 multi-threaded benchmark. That compared to 5966 doesn't seem to be that much. And coming to the 5900X, we see the score jumping to 9054 points. Now that's tremendous considering that's about more than an 800 point increase compared to stock. So again, performance varies across the board from workload to workload. And in Cinebench R20, which is an industry benchmark, we can see significant gains. 800 points is no small task for 5900X, whereas for 5800X, we don't see as much. That's it for this particular AMA on the AMD Ryzen 5000 series. We went through a lot of the processor families, including the actual microarchitecture, its performance impact in gaming, content creation, and quite a lot of other areas. We've gone through plenty of performance graphs, and I hope we've answered most of your questions. If not, please do feel free to put down questions in the comments over here. Again, thank you for joining us, and I hope you have a great day.